hello everyone, my name is Alexandra Nagy and I'm a PhD student at EPFL in Lausanne, Switzerland. And today I would like to talk about my research topic, which is a Quantum Monte Carlo approach to the non-equilibrium steady state of open quantum systems. So in the beginning I would like to say a few words about the non-equilibrium dynamics of this system, and then I will introduce you our Monte Carlo technique to study the steady state. And in the end, I will show you our implementation, benchmarking, and our first results. So the first question is, why are these systems so interesting? And the study of this system gained significant momentum in recent years due to experimental progress in several areas, including ultra-cold atoms in optical lattices, or coupled microcavity arrays, or trapped ions. And the study of this system is interesting because in the steady state, due to the competition between the coherent and incoherent dynamics, we expect a multitude of novel phenomena, including dissipative phase transitions. So, what is an open quantum system? We can imagine a quantum setup which is composed of two subsystems. One is a small system, our system of interest, which is coupled to a large external environment. So, we can very easily imagine it. We have a photonic resonator, we have interaction, we can pump our system, and also we have dissipation. If we imagine now that we know everything there is to know about the system, then our density matrix will evolve by the von Neumann equation. Now, if we want to know the evolution of our subsystem, we have to trace out the reservoir degrees of freedom. And if we make some certain assumptions, we can do this, and we will end up with the Liouville von Neumann master equation. Here, H is our Hamiltonian of our subsystem, gamma is a dissipation rate for some decaying processes, and K's are our operators how our system couples to the environment. If we consider the first two terms, this is going to give us a Schrödinger-like dynamics, except that the decaying states will dissipate exponentially for the system. And our last term is going to take care of the population, which leaked out, and will keep our trace with 1. And we can show that the long-time dynamic of this system will drive us to the non-equilibrium steady state, where we expect this very interesting phenomena appearing. But unfortunately, to simulate these systems is very challenging, because to study the steady state, we have to describe quantum correlations, which, especially when approaching criticality, requires computational resources which scales exponentially with the system size. So our idea was that we try to find a new type of solution to describe these systems. And the idea that we already know that for Hamiltonian systems, we have various Quantum Monte Carlo approaches to use. And to describe the ground state properties in zero-term teacher in particular, this is made possible by the stochastical sampling of the imaginary time Schrödinger equation with the Monte Carlo called projector Monte Carlo. The idea is that now, if we look at the real-time dynamics of our Lagrangian system, it has a common feature with the Hamiltonian one, that in the long-time limit, the eigenstate with the smallest real-part eigenvalue will dominate. So it's quite a natural attempt to try to extend this method. Although we have to consider that the eigenvalue structure of the Lagrangian is quite different from a Hamiltonian one. Our time evolution is not unitary anymore, so we have eigenstates with negative eigenvalues, we have decays. And the empty circle will sign our steady state, which will survive in the infinite time limit. Also, we have a delta spectral gap, which is important because, similarly to quantum phase transitions, this gap will be closing when we have a dissipative phase transition. So, what is this projector Monte Carlo technique? We know that the solution of the imaginary time Schrödinger equation is a series of transients which will decay exponentially. And projector Monte Carlo is a stochastic implementation of the power method, which means that the repeated application of this projector on some initial state will drive our system into the ground state, into the dominant eigenstate of our projector. So this projector can be any function of the Hamiltonian which has one dominant eigenstate. So what is our Monte Carlo? This is called full configuration interaction Quantum Monte Carlo, and it was invented by chemists to molecular dynamic calculations. And it's a type of projector Monte Carlo which uses a linear projector and a complete different sampling strategy. The key dynamical equation for the evolution can be seen here. This is only a finite difference approximation of the imaginary time Schrödinger equation when we project the Hamiltonian and the wave function on a discrete basis set, which means that our walking happens in Hilbert space. We put some walkers on some initial state and we let them walk in the Hilbert space on the discrete basis which we chose. And then the amplitude of a coefficient will be associated with the number of walkers residing there. And now we have a set of dynamical rules which makes sure that we will sample this equation. These rules are applied at every time step for every occupied state. So technically our walkers are not going to walk, but they can spawn other walkers on different states with a stochastically realized probability which will depend on the Hamiltonian element which connects them. Then we will take care of the diagonal step. This will just increase or decrease the population or a given side. And last but not least, annihilation. This means that walkers which has opposite sign, they are annihilated. And I would say this is the most important step in the algorithm, and this will give us an advantage above other Monte Carlo techniques because of the famous sign problem. I don't really have time to talk a lot about this, but this is a very important problem in Quantum Monte Carlo. This gives us the biggest limitation on these techniques. It will appear in the simulation of fermions or frustrated magnets. And since Quantum Monte Carlo is a really large family, it has various manifestations depending on the type we use. In our case, it will appear that we have an undesired state in our system which will grow relative to our signal, to our physical result. So we will get exponential error growth, and we will not be able to see our real signal. So why do we choose FCI equivalency? First off, projector Monte Carlo techniques are especially useful when our Hilbert space is so large that it's impractical or technically impossible to store a vector of the size of the Hilbert space, not talking about matrices. And all these projector techniques get around this memory limitation by storing at any instant of time only a random sample of vector or matrix elements. So this is very useful. And second off, I told you that annihilation is very important because it can be shown that annihilation will affect the evolution only of this undesired signal. So we will be able to reach a stable signal-to-noise ratio. But I have to emphasize here that this will not solve the sign problem. The sign problem is an amply difficult problem, which means it's one of the Millennium Prize problems, so anyone can solve it. We receive $1 million from the Clay Institute. So, because the severity of our sign problem will tell us the minimum required Walker population, which is necessary to suppress the growth of our undesired state. And here comes into picture the parallelization of the algorithm. Because if we are able to implement this code very efficiently, we can reach larger Walker population, which means we can reach larger system sizes. At least that's the idea. Also, this was for Hamiltonian systems. Our idea was to use this to open systems, which means that in this case, we will sample the complex value density matrix. In this case, the walking will happen on the density matrix elements. And also, the biggest difference, we have two Walker populations now, real and imaginary ones. Both of them will evolve, and they have to interact with each other through the real and imaginary matrix elements of the Liouville. Also, I have to tell you here that the solution is not so simple. To make this code work, we needed additional refinement techniques. Because if the steady state has a lot of off-diagonal elements, with magnitudes comparable to the diagonal one, this means that only a small fraction of the whole population will reside on or near diagonal elements. And since almost all of our estimators in which we are interested will get contribution from or near diagonal elements, this will have huge stochastical fluctuation. So I don't have time to go into details, but we used importance sampling initiator approach and problem-specific basis states. But I do have time to tell you that none of these approaches will truncate our Hilbert space. It's still fully available. We let the system decide to go to the states which are important. And we just try to drive that a bit. So about the implementation. I implemented the code in C++ and the parallelization was done with MPI. I used the master-slave architecture, which means I had one node. We took care of the statistics and population control, and all the other nodes were doing the Monte Carlo steps next to each other. The code is very modular. It means that it's very easy to change the system and go to another one because you have to rewrite only one function. So the key for the parallel performance was an efficient and scalable annihilation algorithm. For this, I used the dual hashing procedure. First, all of the state information are stored in hash table, which was needed because during the annihilation, one has to look up almost all the incoming states. And the more important one is I use the hash function for state distribution among the MPI tests. What does it mean? I represent the state, and I will feed the hash function with this state, which will assign it to one of my processes. You can see it on the picture. I have my tests next to each other, all of them with their assigned states, which have plus or minus for per population. The program flow can be seen on this picture too. Everyone next to each other doing the Monte Carlo step. They have newly spawned workers, which are assigned by the hash function to one of the processes. They redistribute it during the communication, and then everyone is working again. It's the same here. So after the Monte Carlo step, everyone has newly spawned states. One of the color is assigned to one of 4 of the processors. After communication, everyone gets their own states. And in the beginning, I thought that I would need additional load balancing techniques, but it turns out that I do not. Since the states and the workers are diluted in Hilbert space, the uniformity of my hashing function ensured a uniform load balance. And the upside of this implementation is that if I increase the population, that will increase my parallel performance. So this simulation was done on a 2-dimensional Heisenberg model, and the simulations are running on our HPC computational cluster. I show you the relative speed up compared to 8 processes as a function of the number of processors used. And each line corresponds to a different worker population. You can see that if I use 10,000 workers, my relative speed up is only 3 times, even with 100 processors. But if I use 100 million workers, my relative speed up is almost 10 times. So, and this is due to the fact that the bigger population I use, the larger fraction of the Hilbert space is spontaneously occupied, so it means the load is more evenly balanced. Everyone is working and they don't waste time on communication. So after I implemented this code for Hamiltonian systems, we wanted to do some benchmarking. For this, we chose a problem without and one with the sign problem. The problem, which is sign problem free, is very easy, the one-dimensional antiferromagnetic Heisenberg model. We know the solution since 1930 by the Wittensets, and what we found that it was a very accurate match with the analytical results. So then we wanted to challenge the code, and we tested it on the 2-dimensional Heisenberg model, where we introduced an additional frustration through the diagonal. And earlier studies showed that the dynamics of this system is very rich, and it shows a variety of phase transitions. We go from Néel order to collinear order, and between the two there are like 5 types of spin liquid states. So I do not have time to show these results here, but again we found a perfect match with the earlier studies, and the run was very fast and efficient even for larger system sizes. I mean like 6x6 or 7x7 lattices. So what we originally wanted to do, to put this on open quantum systems. For this, we chose a very well-studied model. It's the 2-dimensional lattice governed by the Heisenberg XYZ Hamiltonian. So sigma here are polymatrices which act on certain sites, and we have nearest neighbor interaction. We also assume that the system has a dissipation channel which will flip our spins down. To understand the steady state, it's very easy if we first consider the isotropic model in x and y coupling ratio, which means the XXZ, because in this case, the Hamiltonian will conserve the total spin, so it will do nothing to counteract with the dissipation. So we have no magnetization in the xy plane. On the other hand, if we choose the anisotropic model, our Hamiltonian will also have spin-flip terms. It won't reserve the total spin number, so we will have a competition between the coherent and the incoherent dynamics, and this will give us a phase transition. So we will go for a paramagnetic phase in the xy plane to a magnetically organized one. And you can see that in the beginning, our master equation has a Z2 symmetry, which is also spontaneously broken in the magnetically organized phase. So how did we want to study this system? Very recently, Cristiano Ciutti's group presented a study on this system where they tested their new method, which is the corner space renormalization method. So we chose to use the same observables so we can compare our results and our performance. So what we checked the linear answer of our system if we put an external magnetic field on the xy plane, and this will contribute to a Hamiltonian. Our response will be summarized in the susceptibility tensor, and for convenience, it was easier to check only one singular quantity, the angularly average susceptibility. And these are really excellent results, and unfortunately, I cannot show you bigger lattice sizes because 4x4 and 5x5 are still queuing on our cluster. Probably tomorrow they will be done. But I do want to show here that our angularly average susceptibility curve will present a peak which will get sharper and sharper as we increase the system size. And this is due to the fact that, as I told you, similarly to quantum phase transitions, our Liouvillean gap will be closing at the phase boundary, which means that the response of our system won't be linear anymore. And these results are in agreement with Cristiano's result, so what we also expect that once we have larger system sizes, we can do a finite size scaling of the maximum of the peak, and we can get a critical exponent out of it. So, like now, I would like to conclude my talk. In the beginning, I showed you why these systems are so interesting in recent years, but also the simulation represents a major challenge. I told you about our approach, which we try to use now, which is a generalized projector Monte Carlo method. And I showed you our preliminary results, what is done. We have a highly efficient code. We benchmarked it on Hamiltonian lattice models, and now we have results on open ones. And what is in progress? Of course, larger system sizes and different models. For example, probably the driven dissipative Bose-Hubbard is going to be the next one. And, thank you for your attention.
So, questions to the speaker? Yes.
It's not the physics question. So is this annihilation is the only step where your swarm of nuggets, whatever you call them, walkers care about each other? Otherwise, every walker cares about the Hamiltonian, given something.
Yeah, exactly. So if you have a given site, a given state, you just check which other state this walker can be spawned. You do that.
But there is no like exclusion principle or things like that.
No. There is no. These are like coefficients.
Questions?
So, sorry, maybe I missed some points. So, what's the main aim? To get some critical exponents of
To the study of this open system. For the main goal was to show that this method will work, and it will give us good results with good performance. But yes, what we would like to do, because I told you that we try to compare the results with Cristiano Ciutti's results, so we also try to find the same critical exponent to detect a phase transition in this system.
Next question.
Sorry, the question is not related to physics, it's parallelism that you mentioned. Did you run the code on the GPU? It's only CPU?
No, it's only CPU.
And you run it on the cluster, you said. So are the clusters not symmetric?
It depends, because we have 3 different clusters, and it will depend on which one I will submit it, and then how the scheduler will divide it.
So basically the machine, the master node, and there are basically worker node.
Yeah, that's first I wanted to use a hybrid approximation, but since I don't know how the scheduler will distribute my work, I thought that if they are on different nodes, then it would just make it work.
Because I was wondering if you run it on the cluster, basically in the cloud system, for example, but the machines are not the same. Maybe your load balancing doesn't show the basically.
I did not show, but I also did some timing tests. So I was timing each of the processors, and then I compared the results, like if someone is waiting to the other or not.
Yes, and by symmetric, I mean that, for example, if you have a machine, if you have 4 worker nodes, and each of the nodes has the same CPU,
Yes.
and the same memory size, and the same GPU, when you launch the same number of threads of kernel on each of the machines, basically it's an embarrassing parallel programming model. So the load, all of the tasks start at the same time and pretty much finish at the same time.
Yes.
And so the load balancer would be, any load balancer you use would basically divide the task basically in an equivalent model among them. So if you use any machine which is not the same as the other one, for example, if one of the nodes use GPU and the other node don't use the GPU, then the load balancer may show some unbalanced basically proportion of the task which has been.
Yes, but this is not the bottleneck of the code. So probably there could be more optimized versions of this, but the time that you would invest, it wouldn't be worth it. Because the bottleneck is that if you go up with system size, you get such a huge worker population that you will run out of memory. Now I use like 150 cores, but I will need more. So the main problem won't be my load balancing.
One question, how big is big memory? So you said if you run out of memory,
So-
large number of walkers.
So each core has 1 gigabyte memory, and if I don't use enough parallel processes, then they will receive more states which they can store, because in the end I do store a representation of a state. So basically I use a bit set representation which I broke down into a 16-bit integer array, but I have like, in bigger systems I can have 200 million states. And even if I store that with some certain flags and then I distribute it, I run out of the storing memory.
Okay. I will have some other questions. Okay, so let's thank the speaker again.